So my name is EJ Kreinar. I'm going to talk today about the RFNoC neural network library that uses Vivado HLS. I put together for the HLS RFNoC challenge this year. I was team E to the J omega. And if it doesn't get a laugh, I'm not sure that I'm in the right room at this point, because if there's anyone that would ever laugh at that, it would be here. Good, good. All right, so what is it? This is the RFNoC HLS neural net is an out-of-tree module, and the goal is to be able to simulate, synthesize, and run a neural network on an FPGA. And on the right of this slide, I have a framework for what the architecture looks like. And what I'm going to do is first walk you through the context. Why would I choose to do this? Then we're going to look at what it actually takes to use this workflow. I'll introduce kind of some of the concepts of HLS and do a little bit of a live demo. I'll talk about results and talk a little bit about where it'll go from here. So why do it? So if you take a step back and try and think about the context of exactly what it is. So it's machine learning on RF processing is the goal, and then I want to run on an FPGA. So if we look at FPGA and RF processing, that's an old thing. I'm not even going to spend any time on that. Everyone does it. FPGA is a machine learning. Now this is really cool. In the last 2 to 4 years, there's a lot of interest in running FPGAs on machine learning. And I'll say it again, but machine learning neural networks are one of those problems that's embarrassingly parallel. And it's well suited for the sort of accelerations that you get from running on GPUs or running on FPGAs in some cases. And we're seeing kind of an interesting trend where, like Google is doing a lot of machine learning. They want to implement on FPGAs or eventually ASICs for power savings versus GPUs. We've got the Amazon Web Services F1, so there's going to be a cloud ultra-scale available. There's grad schools. UC San Diego is kind of big into the FPGAs for neural networks. There's some commercial stuff, and a lot of times it's focused on image processing, but it's a really cool field in the last couple of years. The bottom one here, machine learning and RF processing, this is also really interesting. It's new. There's early adopter interest. At GNU Radio Conference last year, those of you that were here saw Charles Clancy's talk on machine learning and RF processing. You'll see a talk tomorrow or Thursday from Tim O'Shea about the same field. And recently, in fact, just in August, there's a DARPA BAA that went out for RF machine learning. BAA. So it's kind of there's kind of a wave of interest in doing machine learning. We saw a talk yesterday on it. So it's an interesting time, but there's not really anything that tries to combine all three fields yet. So that's kind of what I'm trying to take a look at with this particular project. The problems here. I saw this meme. I think I saw it for the first time at GNU Radio Conference last year, but I haven't seen it this year, so it's totally applicable and always a good reminder. This is not simply program an FPGA. But let's put it in the context of neural networks. So when you have a neural network, those of you that have worked with neural networks before, I did not before 8-10 months ago. I picked up the Udacity machine learning class, which I highly recommend for all of you in there that are interested in trying it out. It's a pretty good 1 to 2 week sort of thing you can dive into and learn neural networks. And one takeaway I found is that critical to the neural network performance is the architecture. You have to have the right number of layers, the right size layers. You have to have the right type of activation functions. You have to, go from there, essentially. Experiment. You have to test and try different things and see what works. And when you develop something for an FPGA, you want something to be you want it to be optimized. So if you have a one-size-fits-all solution for an FPGA, it's not going to be optimal for any particular case. And in order to change something in the FPGA, if you're doing Verilog, it's a lot of headaches. It's glue code. It's you've got to interact with a processor. You have to trade off these resources versus throughput versus latency, and then all of the wrappers that go around that. So it's a little bit of a headache. And what I wanted to do with this project is provide a solution that allows neural network developers who maybe don't have so much FPGA experience to be able to iterate their solution for their neural network and change the architecture and be able to get a good result on the FPGA. And so when I say efficiently here, I mean it in two different ways. So the first way I mean is it's got to be efficient for their time. So I don't want people to spend much time doing this, and I want it to be resource efficient from the FPGA. So I'll show some benchmarks for the first kind of pass I have at the neural network building blocks. So this leads me to HLS and RFNoC. And if you look between those two tools, what I found is that there's enough of a workflow here that you can start to approach a workflow that efficiently implements FPGA-based neural networks efficiently in time and resources. So again, on the right, you have the framework for what this actually is. It starts in C++. So this uses the HLS tool, implement the neural network in C++, set up the compiler directives and synthesize to HDL, goes to Verilog, and then RFNoC handles the FPGA glue code routing, so attach it to the crossbar, and then there's the drivers that are provided to essentially do your transport mechanism to go out of the FPGA and into some processor, and then you can plug into GNU Radio. So there's this framework here that exists, and a lot of that's there that I wanted to take advantage of here specifically for RF processing. So now let's talk about how to use this. So starting, again, at the bottom, at the core of the project is C++. They have a small library of header functions that implement neural network building blocks. So what are these? These are fully connected layer. So it's basically a FIR filter, essentially. You can think of it in signal processing terms. You have a few convolution layers, so I focused on one-dimensional convolution because they're a little bit easier than two-dimensional convolution, and because when you have IQ, if you want to do an IQ convolution, it's really just a one-dimensional convolution with two channels on the input, and so that kind of has a pretty good analog here. There's activation functions and some max pool operations. So this was the starting point, and it lets me put together a proof of concept sort of scenario where I can show how to develop a neural network, change some of the parameters, and kind of get a baseline performance. And let's see. So when you're doing this development in HLS, the starting point here from the workflow is with the Vivado HLS tool. You're in C++, you put the neural network together. It kind of looks like TensorFlow. So if those of you have used TensorFlow, I'll show you the code for this. If you squint, it looks a little bit like something that you get at TensorFlow. So you have to use your imagination a little bit. But the idea is that you synthesize what the neural network looks like, and then it's run, which is kind of the concept behind a TensorFlow implementation in Python. What that gives you, when you run your simulation, you can do trade-offs between fixed point, floating point. So my typical workflow, which I could show you in the demo, is that I'll start with a reference implementation. So I do a Python in TensorFlow, train your neural network, and now you have some set of training data and results data. Implement the C C++ version of that in the HLS, using the HLS library. Use your inputs and compare versus outputs in floating point. Then make the switch over to fixed point. And the HLS framework makes that really easy. So for me, it was a process of, it never works the first time in the floating point to fixed point conversion, and tweak some data types, and it'll get to where you want it to be, at least in the applications that I've used. And then it's synthesized. And on here, let's see, this was a convolution network and was out of context, but it's got good resources. So if we want to look at what some of the baseline resources were, in the neural network library, I've tried to provide a few default synthesis options. So with HLS, equally important to the C code is the compiler directives that tell your compiler how to unroll a loop. So basically, if you're thinking in terms of FPGA fabric, what's your pipelining look like? How many multipliers do you use at each step? And so I've tried to do a middle-of-the-road comparison that hits that inflection point of resources versus throughput. And if you want to get better, it's possible, but it's tweaked for an application. So I just started with the middle-of-the-road thing here. A couple call-outs. The top of fully connected layer, 40 by 40. My example that I'm going to show, I'm using 5 of these layers. These are really reasonable amounts of resource usage for what it is. If you get a bigger fully connected layer, the amount of weights just scales up, and I'm using the E300, which is mostly for just a demo platform. I wanted to show this running on something embedded rather than something like an X300, because an X300, you could generally pull the data off and process it on your laptop or your desktop. Whereas the really cool application to me is if you can walk around with your E300, run something at 40 megahertz, do a neural network at that rate, and have that running in the FPGA on the USERP E312 or E300. But unfortunately, the block RAMs, your coefficients are just, this is the max of what the E300 can handle. So you kind of get into a limitation with block RAMs. We talked about some other options for that later. The convolutions, they're pretty good. They do run a little high on flip-flops and lookup tables. For this particular one, it's storing the neural network taps inside Fabric. So it's not great, but that could be optimized too. Another interesting call out is the activation functions in the max pool is essentially free. So these, to give you some context, the flip-flops and lookup tables for the fully connected layer is like 1% of the E300, and so this is just a trivial amount. So you're pretty much going to be taking up your block RAMs with your big fully connected layers and your fabric with your convolution layers. So if you think about it, if you're familiar with FPGAs, it's not too much of a surprise here. This is kind of what you expect, and it's decent performance for what it is. Okay, next, let's say you synthesize your compute module. So if you're looking at this, we started with C++ code. We have now jumped over to synthesized HDL. This is at the output of the tool. And now we need to bring this into, actually put it onto the FPGA. So this is where we go into the RFNoC framework. I have a little wrapper that goes between the RFNoC and then the output of the HLS. And the real purpose of this is that your packet sizes for neural network are kind of arbitrary. And so you need to do a little bit of intelligence to be able to wrap that correctly to play nice with RFNoC. So I try and provide that. This is it's still being improved right now, actually, for performance. But it has a good start. But now that you have everything in an RFNoC compute engine, a benefit here is that you can run the RFNoC test bench simulation, put it in the FPGA development workflow that you'll be used to if you've been doing RFNoC development, and do a simulation, see the scope outputs, and basically make a FPGA test bench for this. And there have been several occasions in the past couple months where that has exposed problems with the HLS synthesis that did not show up with the HLS tool. So it's a good sanity check, and it works really well. After the FPGA, so you've built your RFNoC compute engine, you've simulated in your test bench. Now you can build that into an FPGA image to target your E300 or your X300. And then how do you get back to the processor? You can you take advantage of the UHD framework that provides that data transfer for you, whether it's over the DMA between the AXI FPGA and the processor, or over the Ethernet transport. It's taking advantage of UHD there, and it plugs. You have the GNU Radio Companion to be able to set up your application and run it. Now there is some data type wrangling, so this goes back a little bit to the wrapper that's being improved. I'll get rid of this data type wrangling, but it still works. So the takeaway here is that the idea is you as a developer don't have to do that FPGA to processor tedium. Now, what's provided in the out-of-tree module? I want this to be inspiration. So, like I said, after I did this Udacity course, I realized that if I just do a specific application, it's not really that useful in the larger context of things because it's too optimized. Other people's neural networks are going to be different. So I provided some examples as inspiration. The top two are based on that Udacity machine learning course. So there's kind of a silly little image classification problem where you get the letters A through J, and you have a neural network that classifies these. And it's a fun little project, and you work through 1 layer to 2 layer to convolutions. And so I started off by implementing the 1 layer and 2 layers with this HLS library and confirming input versus output on the pre-trained network. So for both of these, I have this the HLS implementation. And then for the 1 layer, the 2 layer is too big for the E300. But for the 1 layer, I pulled that into an RFNoC and GRC. I have a little test application that runs on the E300. And then the other two that I'm a little bit more excited about, obviously, are the RF processing. So number 3 is a neural network that's based on my colleague Derek Kalmoto's work. He presented last year. He'll be presenting again tomorrow on modulation recognition, where you calculate some set of features on streaming RF data and then feed that into a neural network. So I have, he provided some example data for that. So I have the HLS implementation. I have the FPGA and a GNU Radio Companion implementation that runs on the E300. And the last example here is a convolutional network for modulation recognition of streaming IQ data. So if you have a streaming, just raw stream of IQ at some X sample rate, this is the architecture for this network is a couple convolution networks, a couple max pools, and then a few fully connected layers. And I don't have test data for this one, so I haven't pulled that through all the way to the final result. But it does fit in the E300 as implemented in the HLS. Now, to work on in the future, some things that need work. More neural network types would be great, more building blocks. 2D convolution is all the rage for image processing. Recurrent networks are also useful in some situations. Really fleshing that out as well as optimizing for different scenarios, the blocks that currently exist. Another drawback is the programmable, well, currently weights have to be hard-coded into HLS. And based on a limitation of HLS, they in fact have to be encoded into the C++ code. So there's not really, they have to be known at compile time, and there's not really a runtime way to do that. So, so we could make them programmable, but then it would involve drivers on the C++, FPGA, and software. So that's kind of like a little bit of a stretch goal. Well, the weight storage is another interesting problem. The HLS uses some smaller VRAMs. It doesn't use the full VRAM size. And on the E310 particularly, you have this gigantic FPGA dedicated off-chip RAM. If you could use that, that would really be able to store a lot more weights. So you'd have a lot bigger networks, and that would be awesome. But that's definitely like another order of magnitude difficulty. Okay. So I do have, let's see, how much time do I have? So 10 minutes or so? Okay. Okay, so I do have an E312 here, and I'll just show you some subset of a live demo. And just to give some context on this, it's still a demonstration application. I'm using the expert features that are pre-calculated, and I'm running it through an FPGA and the FPGA on the E300, and then I've set up UDP to send the results back to my laptop, and then I can do a little raster plot of the results. So here's my raster, and then let's see, SSH here, demo. Okay. Okay, and hopefully this will work. Okay, so there's some classified modulation recognition. So you know, it's just a cute little demo with some visualization. I've confirmed with Derek the last 4 classifiers are not really used here. So what I'm doing on the flow graph side, just for reference. On the desktop, I have a little softmax operation that runs on the output of the neural network, and then that's being plotted in this raster plot to show what the results are classified as. And it's really just shoving the data through the FPGA, sending it to the processor sends it back to my laptop, and it's plotted here using GNU Radio. So kind of an interesting little demo application. The other thing that might be interesting is to just show a little bit of what the HLS workflow looks a little bit like. So right now I'm in the modulation recognition example, and let's see. So the reason I want to show this is because it's kind of an interesting workflow, and it helps, I think, to get some, if you're interested at all in using it, it helps to get some perspective on you know, best practices to some extent, you know, what works, maybe what doesn't work. And what I found here code-wise, so I'll show you the block. So the modrec block, this is using the neural network headers, neural net library, the header library. And each of these chunks of code here represents a layer. So there's a fully connected compute layer, and then followed by a ReLU. So this is heavily templatized stuff here. So this is why I say if you squint and kind of ignore these templates, you can pretend that it looks a little bit like TensorFlow in that you're declaring this ahead of time. The reason it's templatized is because you need to know all of this at compile time for the HLS compiler to play nice with everything. But it's parameter.
Can you increase the font size a little?
Oh, sure. Is that better? Okay. Okay. So yes. So each block here represents a layer. In the neural network, we have a fully connected layer followed by a ReLU, templatized to be able to specify data types and specify network sizes. And the interesting thing about putting the data types into the template is that I'm able to have a header file that just contains the data types. So I have these type defs here that are using a fixed point implementation. So HLS abstracts away the details behind changing fixed point data types, which is nice. But in C, you can oh darn, you can change this. So now this is going to use the floating point data types. And so I'll do my simulation starting with the floating point data types, confirm that the results work. Oh, and it appears that Vivado wants to come up, at least on this desktop. But and then you swap this out and use the fixed point data types to be able to optimize what that is. That helps your workflow a lot before you can synthesize. With that, I think I'll open it up for questions. Yeah.
None? There we go. We have one at the back, and we have one over there. So who has the second mic?
Okay, so interesting work. I just have actually 2 questions. One, regarding your experience switching it from floating point to fixed point. Was it through a simulation that made that decision on like the range of your numbers, what will be the bit width that you're using, or is it just a direct mapping, which I guess is the case based on your data type, or
Yeah,
like or the fixed point. So that's the first question.
Yeah, so it is based on simulation. So the way I've tried to structure these examples is that I'll simulate on like a golden data set and do that simulation using the floating point. And then that gives me a reference. So I know that it works in floating point, and then switch the data types to the fixed point. And honestly, every one I did, it didn't work to start out with. And so then that's kind of a really good spot to be in, because then you can go back and tweak what these data types are. And this network is a good example. And let's see if I can even, I'll blow this up even a little bit more. So you'll see I changed, so I tried to reuse this accumulator data type, 32-bit integer width and 6-bit integer width, and then the rest is fractional. And then I found there's an overflow in like the 5th accumulator. So this was a situation where I wanted to keep the fractional width for accumulators 1 through 4, but I wanted to change the width on the last one. So that was one of the, you can go through and do this iterative process where compare the simulation results to what the gold reference is, and track down what those problems are in the conversion.
Okay, and the second question regarding the need for the wrapper that you mentioned, is it because you have too many inputs that the XI interface cannot handle? Because I know Vivado HLS can actually abstract that for you. If you specify the interface to be XI interface, it will automatically create the buffer for you and does it. So why did you need to do
that's
the
a good
wrapper?
question. So that gets into how the RFNoC expects packets. So on the AXI bus, inside the AXI wrapper, RFNoC is if you're using, so what's called simple mode is that you assume that the number of samples going to your logic or the number of samples coming out of your logic is exactly the same as the number of samples going into your logic. So if you do simple mode, it's quite easy to do the use just the AXI stream interfaces, which I do use. But if you don't have the same number of samples out as the same number of samples in, then you have to manipulate the header for the RFNoC Vita format. So that wrapper is meant to manipulate the header. And also, what I'm working on right now is that the reason, I need to improve the performance, but you do get 32 bits in the coming out of the AXI wrapper. And so for the neural networks I've implemented here, you only assume 16 bits on the input. So I want to deserialize that and reserialize that to improve the efficiency. So it's a little bit of just kind of infrastructure stuff that I would just rather have wrapped up and obfuscated from me if I'm using it.
Quick question. Regarding the HLS tool, is it freely available or needs to be purchased or something?
Oh yes, it is freely available. Yeah.
So if you have Vivado, you also have HLS.
Yes. Yeah. Well, certainly for the E300, it's a Webpack license, so you get it. Yeah.
I guess we can answer one more question. But I don't see any. Okay. Well, thank you very much.
Thank you.